Good evening, everyone, and welcome to Straight Science. Straight Science is a evening seminar series put on by University of Alaska Fairbanks Northwest Campus in Nome, Alaska, and also University of Alaska Fairbanks Alaska Sea Grant. You're in the home office tonight. And both Northwest Campus and Alaska Sea Grant, we are public servants of the Bering Strait region. We serve all peoples of the Bering Strait region, which is the homeland and waters of the Inupiaq, St. Lawrence Island Yupik, and Central Yupik peoples. So tonight, no stranger to straight science, we have Jim Thomson. He is a researcher or a physical oceanographer. He's studying the physical properties of the ocean. He's with the University of Washington Applied Physics Lab and a professor of civil and environmental engineering. So he's going to tell it to us straight up. And he is no stranger to straight science. So I was looking up how many he's done, and he's always on the topic of waves or storms and the water currents going through the strait. This is his fifth straight science, and he started doing these in 2015. So, Jim, we're really grateful to you to always, one, be studying in this region, but also bringing it back to us again and again and again so that we get to keep up with all your findings. And I think with that, I'm going to hand it right on over to you and we'll get her underway. So we're so glad you're here. Thank you so much.
Great. Thanks a lot. I'm definitely happy to be here, and I'm sorry I can't come in person, but I'll definitely be passing through sometime next year, and really enjoy being in Nome, and we're happy to do an in-person version and update some things when I'm there next time. And we could call it next year. We could call it a 10-year anniversary tour of my first few trips to Nome. I think my first time to Nome was 2014, so it's already been 10 years, maybe. Hopefully, I have a couple new things to tell you. And then I also tried to keep it on the shorter side so there'd be lots of time for questions and discussion, just to hear from you and what you're seeing in the region. And I think there's just so much happening right now, and you get these really big storm patterns and things coming through that hopefully there is something to talk about. So I want to start with just a video, and in terms of the science and the things that I study, if you come away with an understanding of this video, then I think you have a general sense of what I work on and what I'm interested in up in your region. And this is a video of what we call the marginal ice zone, so the edge of the ice. This one's taken pretty far offshore. It's in deeper water, but it has the same things that you would see if you're near the coast, and probably a lot of you see it all the time. You got some open water in the distance, and the winds are up. Maybe it's blowing 15, 20 knots. There's some whitecaps out there, and that's made some waves. And as the waves come in, they get to the edge of the ice, and right at the edge of the ice, they cause a lot of motion in the ice, right? The ice is moving pretty vigorously, kind of in the middle of the video. And then as you look closer and closer into the video, then things aren't moving very much, right? If you get all the way in where this video is taken from a research vessel from the Sikuliaq, which you would have seen in Port of Nome pretty regularly. Where the boat is in this video, there's not that much motion. And what we have a couple different ways we describe that. We call that the attenuation of the waves coming into the ice, or we call it damping. And basically the sea ice damps the waves. And that's a well-known phenomenon. And a lot of our work is to try to quantify that, try to understand that well enough that we could put it into the forecasts and then be able to say, well, on this day you'll have more waves because there's less ice, and on this other day you'll have less waves because there's more ice, and back and forth. And then to understand how the two things work together, because one of the things that will happen over time in a video like this is that the waves will take all the ice, if it's kind of a messy ice edge, and they'll compact it, and they'll make a really sharp, crisp ice edge because the waves are slowly moving all the ice together and making a compact ice edge. So there's those kind of things, we call them feedback mechanisms, that we want to be able to better understand, so we have some ability to predict them into the future. So I think that video really sets the stage. That's some of the things I'm looking at. But I also want to talk about just the whole region, the whole Arctic, not just the Bering Strait region. And To do that, I just have to start with that there's less ice, and you all are very well aware of it. There's less ice in every way you want to count it. There's less ice when you look down on top of the Arctic. Here's Alaska. There's Nome in there, Bering Strait. And if you look down on top and you ask how much ice is left at the end of September, which is usually the minimum, there's a lot less ice. And the orange line is where the ice edge used to be back in the 80s and 90s, 2000s. And then the amount of ice that actually is there, and this is a 2020 example, but you could pick just about any year in the last decade and you'd get a similar story. This is the ice that remains. And there's a huge expanse of open water that didn't used to be there in September. And that's really changing the dynamics of the region pretty dramatically. Every year's a little different, but that's kind of the overall story. Okay, that's just the surface area. That's just looking down from above. This is a satellite result. But there's all these other things that you could use to quantify how much less ice there is. There's the thickness of the ice. It's a lot less thick. You multiply that by the area, you get the volume. And so there's less volume of ice. That's important. The ice type is changing, the strength of the ice, concentrations of the ice, the rheology of the ice, how the ice responds mechanically, that's all changing, getting weaker, getting looser ice. Those are big changes. And then there's also the how things evolve in time. This is just a snapshot at the end of September, but we know that the ice is retreating much earlier in the spring, almost 2 months earlier in some cases at some locations than it was in the 80s. That's really dramatic. And then it's advancing much later in the fall, about a month later than it was in the 80s. So those are really dramatic changes in the length of time that there's open water. So there's a lot less ice in time and space. That means there's a lot more open water in time and space. And the thing that's really clear out of that is that when there's less ice, there's more waves. And that's just a simple thing about real estate. There's space for those waves to form. So this is an analysis that's a pretty classic analysis that we've published a bunch, and a lot of other people have used a similar idea. And you look at the energy that's in the ocean surface waves, and you look at that as a function on the bottom axis here of how much space there is. And that space we call the fetch. So fetch just means the distance over which waves can be formed. So the distance over which the wind is pushing on the ocean. And the simple idea is if there's more space, there's more waves. The data that we're showing here is from a full year of data collected in the middle of the Beaufort Sea. So a bit further north than the Nome, but still representative. And still really driven by how much ice there is. If there's a lot of ice, then there's not much space. Fetch is really small. You're down in this part of the graph. And if the ice all goes away and there's tons of open water, then you're up at this part of the graph up here. Okay, well, what we get from all of that is we get more coastal impacts. So I could pick a lot of different pictures to show. Gay was just showing me some pictures from Kotzebue from 2 weeks ago, the big storm that came through and flooded the whole town and made a mess. And there's just a lot of those pictures now from all over the slope and all over the region. So this is one particular one that I had handy. That's Utqiagvik in September 2017. And you see these big waves coming in the coast here. I think this would be Steveston Road over here is underwater, and these houses are underwater. These ice cellars are flooded. This is a real mess, right? This is a real problem. And part of the reason this is more common now is because there's all this space with less ice in which the waves can generate. And this is something that it's important to note that there's some non-local effect here. You could have a really strong storm with really strong winds. It's blowing 60 knots at your spot. And in the 80s, 70s, old times, you wouldn't have such big waves from that because the ice was close. Maybe not close enough you could see it. Maybe it's still 30, 40, 50 miles away. But now that it's hundreds of miles away, it has all this extra space for the storm to build the waves over all this space. And this is a place where over these large distances, a lot of energy can be accumulated in the wave field from the wind. And that requires a lot of space for that to happen. And then all of that gets unloaded at the coastline. So you get a much more dramatic amount of energy arriving at the coast, even for the same wind. So you may not notice that the storm's any worse in terms of wind, but it's a lot worse in terms of the coastal impact, in terms of the waves arriving at the coast. And that's because of this much larger scale pattern in the ice. So whether or not there's open water 200 miles from your location instead of 40, that can really change what you experience at your location. And that's the important distinction here. Okay, so overall, less ice, more waves, and then more coastal impact. And we should unfortunately expect images like this one to happen more often. I can't tell you exactly how many. I can't tell you exactly what it's going to look like, but in general, more. And here's some other examples. This is one that I just remember. I was on a ship that had left from Nome just before this event, so I'm sure everyone there is familiar with this typhoon that came through in 2022. It was pretty severe, and this is an example of having a big response here because of the storm that came through and had all this space out here in the Bering to generate a big wave field and made these enormous waves. At the time, one of the seated buoys was still deployed off of here. I understand the station's not active anymore, which is that's really a shame because it was a nice amount of data that was being collected there. You can see the buoy reported waves that were 5 meters, so that's more than 15 feet, even though the forecast was only 3 meters, so 9 feet. That's a big difference, right? Just in terms of the height of the waves and the amount of energy carried in the waves, which is really what is the important metric for erosion and for coastal impacts. The energy goes with the wave height squared. So you're looking at something that's almost off by a factor of 2 in energy or in wave height. And then that would be a factor of 4 in wave energy. So this is a big difference. And this means that our models and our forecasts aren't yet don't have enough as much skill as they should to be able to forecast this. And obviously this had a huge impact. I came back to the Nome about 2 weeks after this event, and wow, that was tough for you all. So I just wanted to note that has some of the same features in it, even though at this time of year you never would expect sea ice down here in the Bering, but it's still got that same idea of accumulating all the wind's energy over this space that turns into waves and then arrives at the coast. Okay, I want to talk about measurements, how we know some of this stuff, what the kind of measurements we make. Most of this we do with buoys. So I'm going to tell you about a whole bunch of different buoys that we use. And most of these we make ourselves at the University of Washington at the Applied Physics Lab. So here's an example of a bunch of them, some deployed in the ice. Here's a fun picture using a robot to look underneath the ice and look up at the buoy and see what it looks like when the buoy's trapped in some ice. And then there's me on a regular day at the office, picking up one of these buoys that has been out for a while and out in a storm that has really strong icing. So we were just talking right before we started the meeting about how the next storm that comes through, it's going to be strong winds and the temperatures are going to be right around freezing, and you might get a fair bit of freezing spray and icing. And you get that on the ships, you get that on the railings, you also get it on the buoys, and it causes all sorts of problems. So we have that issue too with these buoys, but they move up and down with the waves and they measure the waves, and that's how we get some of this information. We also do it with moorings, and again, this is pretty far north of your spot, but I want to tell you about these moorings because I think it's a pretty remarkable data set we have now. So these are up in the center of the Beaufort Gyre. It's part of something called the Beaufort Gyre Observing System. This is a big collaboration with the Woods Hole Oceanographic Institution. You've heard from those folks from time to time, I imagine. National Science Foundation is paying for it. And then on our part, we've added some wave measurements to these moorings. So here are the locations, the green and the blue, that's where they are. And the moorings stay out year round, and they get serviced once a year, usually in September. They are below the surface. So if you were there on a ship, you wouldn't see them. And they're below the surface so they can survive the winter when the ice is on top. The site is quite deep. Each of these locations is about 3,000 meters deep. And the mooring goes from the bottom up until almost the surface, stops at about 30 or 40 meters below the surface, depending on the design, because that's about the deepest we ever see any sea ice coming through when you have these pressure ridges and ice keels that come through. So that keeps the mooring safe throughout the winter. And then they have a small acoustic sensor. It's a little bit like a fish finder you'd have on a boat. And that fish finder is pointed up, so it sees the bottom of the ice. You can see when the ice is there, and then can also see when waves are there. So we can use that over the course of many years to measure the wave heights every summer when it's open water, and the ice thickness every winter when the ice comes back in. And you see this really strong seasonal pattern, right? You see waves in the summers mostly, you see ice in the winters, obviously, and you see it grow and melt. You see a couple summers without waves because there have been a few summers where there's been some ice that stays over these sites, so they don't always become ice-free every single summer, because year to year things vary a lot. But certainly they're much more often ice-free than they were 20, 30 years ago. That's a big difference. So this is also some of the data we used, and we use it to look at these large-scale patterns. And remember, my point is that the large-scale patterns still affect you at the coastline. If you live in Reykjavik, if you live in Wainwright, if you live in Nome, these things that seem like they're far away, sometimes they can still have a big effect on how big the waves get by the time they arrive at your beach. So here's some of the trends that we're seeing from that data set. This is a trend that goes back a little bit further because we have model data that we can use to extrapolate back here. So this goes from 1990 all the way through to 2015. And we see these pretty strong trends where wave heights are increasing over the whole area. The years go up and down, but they're increasing. Wave periods are also increasing. So wave period, that's the distance in time between each crest, between each wave that comes through. And that's actually related to the same thing. That's related to the waves having more space and time to evolve. Those waves, because they can evolve, they tend to get longer, or sometimes we say they get more mature. It's like they grow up. What it really means is they're carrying even more energy to the beach, because that's another factor in how much energy is arriving at the beach. So a longer wave period, that's also something that causes more impact when it gets to the coastline, causes more erosion. The interesting trend here is that the wind speed is pretty flat. So in general, we have not seen a strong trend in how stormy it is in the region. Even though I know probably living there, you feel like there are more frequent storms, and the storms have more impact. I think there's some active work on that right now, and I think there is an emergence of a trend there. But the thing to note is you don't need a trend in the wind speed to have more waves. You just need more space. So if you kept the winds all the same everywhere and you just took the ice away, you'd have a lot more waves. So that's where these things are compounding effects that are changing the climate and changing the experience you have as a coastal community. And even without a change in wind speed, there's a bigger effect. Okay, there's also this change in the seasonality. So we already mentioned that when we talked about the ice, but the waves go in lockstep with that. So here's an example from a coastal site over, this one's close to Kaktovik, and here is these histograms of the number of observations of waves of a certain height, and the colors tell you the time of year. So the August and September, that's the blue and the teal, and those are kind of what we would have expected from prior measurements in prior decades. Waves are 1 to 2 meters, so 3 to 6 feet, and there's not too much happening out here at these really big waves. The change we're seeing now is now in October, we're seeing waves which we wouldn't have seen at all before because it would be ice covered and there'd be no waves. And now we're seeing waves that get up to 3 or 4 meters. So now we're like, 9 feet, 12 feet, right? Much higher waves. And they're persisting later in the storm, or later in the season when the storms come through. So part of this distinction about is it stormier or not is really about, are the storms, the strong fall storms, are they coinciding with open water where they can make waves, or are they coinciding with ice when they can't make waves? So, and you can get some pretty big changes if you just suddenly don't have ice when you used to, and you have a big storm come through. Okay, so we see, that in the data, if we look for some simple trends, we look for the average wave height in a given year and the average ice thickness in a given year. Those two things are related. So this is 12 years of data from those moorings. And, there's scatter. It's not a perfect one-to-one thing, but in general, if you have a year with a lot of waves, it's a year with a lot less ice. And if you have a year with thicker ice and more ice, then it's less waves. They go together. Almost so much that one could predict the other. I mean, but we know that seasonal ice predictions are pretty tough. But if you got a year with a lot less ice, you're probably going to have a lot of waves. Okay, that's what we've been doing for the last 5, 10 years or so. Now I want to shift gears and keep kind of telling you the same information, but with really the stuff we're doing right now that we've been doing this past year and that we'll be doing in the upcoming years. And that's to deploy more of these buoys, but to do it from an airplane. So these are these air deployed buoys we call micro swifts. They're micro because they're small and they can fit out of the airplane. These are the deployments we've done so far. So we've done, let's see, a total of 28 of these buoys. These are the people that are we're doing the work together as a collaboration. This is Mike Steele. He gave a Straight Science a little while ago, and then Giselle Zhang from NOAA and UW, and she was there also and presented. And so she handles all the aircraft logistics and a lot of the other science that's happening from the aircraft, including doing harmful algal bloom work and all these other things. Mike's got a lot of expertise in the sea ice and what the ocean's doing. So we're all working together and trying to use these data sets together so that when we do deployments, we get as much bang for the buck as we can out of the data. Here's what it actually looks like. This video is underneath the belly of the plane, and this is one of the buoys getting deployed out of the tube of the plane. So the plane flies around, we pick the waypoints, the locations, and when we get over that spot, we send it out of the tube, and then the little parachute deploys. And that parachute, keeps it straight on the way down and makes it land not too hard on the water or the ice. And we do this over ice too, and they mostly survive. Every now and then one doesn't work, but they mostly work. So this is what we've been doing this year. And here's a little bit more detail about the buoy. So it's about ½ meter long, and it's got alkaline batteries in it, not lithium batteries, because that's a pain and a little more dangerous. So we stick to the alkaline. It has a transmitter, so we get all the data back. And if it's not recovered, we still get the data back. This is what it looks like in the lab when it's ready to go, and this is what it looks like when it's floating around. So if you see it floating around like this, where you're out fishing or hunting or whatnot, you can just let it be. It's good. It's getting data. It's doing what it needs to do. But if you see it like this on a beach, please do pick it up. And there should be a phone number on it. You can get in touch with Gay, who knows everything that's happening in the region, and she'll know to call me, or you can call my phone number right there. And we'll be happy to help you return it, happy to pay for the return. We've got a great hat with a nice logo on it. We'll send you as a thank you, and we'll definitely make it worth your while. So if we do get them back, that's a great thing because we can reuse them. We can get some additional data off them that's not sent over the transmitter, and we can just do more science with them. So keep your eye out as you're going up and down the beach for these. We had one get really close to Nome this year, and then it kind of got swirled away back into the Bering Strait currents and didn't actually land on the beach. But boy, I sure thought it was going for the beach. So it's probably going to happen in the future. We have put these all over the region. So here's a quick map of where they've been. Again, we've done deployments these last 2 years. So we did 2023 and 2024. We did them in the spring and in the fall. In the springtime, we've been focused on your region down in the Bering Strait. We've put them up here, we put them over here, and they just drift. So they go wherever the currents take them. And along the way, they measure the wave heights. That's what is shown in meters here. That's the color. So the blue are small waves, the yellow are large waves. And then they measure the temperature and salinity. And we're using that to keep track of the water. And in the future, they may also measure chlorophyll and help us with harmful algal blooms and bloom detection. That's a proposal that we're working on now that hasn't been funded yet, but we're pretty excited about that work because we think we can use the same platform to do more. You can see that the colors here with the wave heights, they vary kind of all over the place. But I will point out that in general, the brighter colors are up here because these are the ones that were deployed in the fall. And remember, the fall is when there's the least amount of ice. So if you have a storm come through with a lot of wind in the fall, it's likely to make the biggest waves because there's the least amount of ice in September relative to early in the season. Look at this right here. These are the ones that were deployed in June of this year. And there was a whole bunch of ice still around this zone. And so waves couldn't get very big because there's all that ice. Here's a distribution of the wave heights. And this is one of the things we're trying to build up over time is an overall climatology or understanding of how big are the waves in the region. And where that would come in is if you're doing design work and you say, well, like the port expansion at Nome, if you want to design those kind of structures at the coast, you need as much data as you can get about how big the waves are and kind of what's the worst case scenario for waves. And so this is one way to get that kind of data and get it in a way that's distributed around the region and start to build up an understanding of how big the waves can get, and they can get up to about 5 meters, which I have to say is that's pretty new number. I think 10 years ago, if you'd asked me what's the biggest waves you can get in this region, I would have said 4 meters, and now I'd say 5 or 6. So that is changing. Uh, okay, here's a detailed example of that one from the spring that I was talking about. And so here is a map. There's Nome down there. There's Kotz, and here are the colors are the marginal ice zone is the yellow, and then the sort of 100% ice is the red, the full pack ice. And so we deployed in late May, very early June, a few buoys right around here. And here are some of the things we saw. We saw that the salinity was low and the water temperatures were low, right about the freezing point. And that's a really classic indicator that you're close to the sea ice, that temperatures are near the freezing point, and also it's a little fresher, it's a little bit less salty, because the ice is probably melting a little bit in the springtime, and it releases some fresh water when it melts. And then this is the more complicated thing to look at. This is what we call a spectrogram of the waves, and this is more complicated than just the wave height. This is having us look at how much wave energy there is, all partitioned or picked apart by the frequency of the waves. So this lets us understand all the different components in the wave field, and then this lets us see as a spectrogram how it evolves in time. And really the only thing you need to worry about there is, or understand there is, this weird stripe here that looks pretty different, right? And it's not bad data. That is real data. That's when this buoy drifted into this tongue of ice, and then a few hours later it drifted out of it. So for a little while temperatures are very cold, salinities are lower, the wave spectrum looks different, the waves are damped by the ice, just like in that first video that I started with. And then the buoy drifts out of that region and back into more open water, and you see the water temps come up, and all the signals of the ice go away. Okay, so that's what it looked like in your region this spring, and there was quite a bit of that, and that's more of that same phenomenon where the waves are smaller in the ice. Now I want to talk a little bit about landfast ice specifically, because a lot of what I've been talking about is kind of this regional pattern, all of this stuff out here. But landfast ice has some unique features, and I think is really important to how a coastline actually evolves and what you experience at the coastline. So here's a nice example. This is at Icy Cape, so it's between Point Lay and Wainwright, and this is some data we collected a few years ago in 2020. And this is a satellite radar image looking down at the site. The whole box here is, I think it's 5 kilometers by 5 kilometers. Oh no, actually it's bigger than that. Sorry, it's 10 by 10 kilometers. And this is in 2020, May 25th. So it's springtime, and there's open water offshore, and there's landfast ice hugging the coast. And of course, this, living in the region, that's a common thing in the springtime, right? We'll have the fast ice sticks around by the coast for an extra week or a month, longer than the rest of the ice. And the pack ice will move out and start to retreat, but the landfast ice will stick around, especially if it's grounded, and depending on how it evolved over the course of the winter, it can be pretty thick, it can be pretty serious stuff, and it'll stay around longer. And that really matters for what the coastline experience is, because if you design an experiment, as we did in 2020, and you put one sensor out here and one sensor underneath the landfast ice, and you measure the waves over the entire season between these two locations, you get a very different signal out here at the orange dot than you do at the blue dot. So at the orange dot, outside of the landfast ice zone, you start seeing wave signals in May. And those waves are 1 meters, 2 meters, up, down, storms come and go. But there's some real, 2 meters, there's some significant events that come through. And that happens for a couple months without anything happening at that blue dot, because the landfast ice in this particular year stayed that whole time. And then eventually that landfast ice breaks out, it goes away. Usually goes away pretty quickly, kind of all at once. It's been sort of rotting in place, and then it's gone. And then in this case, at the beginning of July, then it goes away and the waves pick up. And then all of a sudden that blue dot starts to more or less just match the orange dot. So it's like a light switch, right? When the fast ice is there, no waves, complete 100% damping, attenuation of those waves. And then when the ice goes away, the waves pick up and they get right back up to the maximum level, and they match what's offshore. If you take that data and you make a cumulative calculation and you say, for every day there's a 1 meter wave at this beach or at this site, I'll call that one wave height day. And I'll do it again the next day, and I'll do it again the next day. And I'm going to add it up over the whole season. And what you're adding up is the total coastal wave exposure, how much waves are reaching the coast. And there's a huge difference outside of the landfast ice and inside of the landfast ice. So outside of landfast ice, you would get to something like 60 wave height days by the end of the summer. And inside, with that landfast ice effect, you'd only get to 30. So factor of 2 difference. Why am I telling you this? You certainly already know it if you spend time in these regions and live in this region. You already know this is what landfast ice does. I'm telling you this because it's missing from almost all of our scientific models. Almost all of our models that forecast the conditions in the region or that try to do long-term climate scale predictions and reanalysis of what has happened in the past. Almost all of them are missing landfast ice because landfast ice is really local. It just happens right at the coast. It has, an extent of a few miles at most. So it's a hard thing to include in the way we simulate this and the way we forecast this, because it gets stuck to the land and the coast. It gets grounded. So that's a whole different set of phenomenon that happen. That's not, what happens to the offshore sea ice. And it's at a pretty small scale. And if you're trying to run a model of the whole climate of the whole globe for decades and decades, you just don't have the computing power to take care of the little thing happening by the coast. So if I do this analysis and I ask this product called ERA5, this ERA5 is a large-scale climate model that a lot of people use. And I ask ERA5 with its data, what is the coastal exposure along the North Slope of Alaska from the 80s up to present time? I get this enormous trend line here in the orange. But that climate model has no landfast ice. It doesn't know the landfast ice is there at all. So that's wrong. How wrong is it? Well, that's what the blue line tells you. If we introduce a landfast ice mask onto that model and we use it, we only do it back until 2007 because we only have a landfast ice data set that goes back that far. There's another one that's going to be available soon, and we could probably redo this analysis. But the time we did this, that's all we had. Now you get these blue dots, and now you get something that is a more accurate picture. There's still an increasing trend. So this is still cause for concern. There's more wave exposure along the coast, and it's increasing on average each year, but it's not increasing as fast, and it historically was not as high as we think, or as you would think from that large-scale model. So this is where we spend time getting measurements that are local and that are really tuned to the right questions, and we get a better answer, and we have more information then we can look to the future. And that's what we're really trying to do here. And I think that if you gave me a magic wand and said I could fix one thing in the climate models with an eye towards, knowing more at the coast, I would say we've got to get to landfast ice right. That's my magic wand. We could predict and understand landfast ice better, then we'd do a lot better with all of this. Okay. I want to wrap up soon, just tell you a couple other things. I want to tell you about some fun new technologies that we're exploring and that you may hear about and see around the region. And one is using seafloor fiber optic cables. So you're probably familiar with Quintillion. They're the company that brought this cable around the North Slope. And here's the original map, and this is an old map now. You can see this is their phase build out. So 2017, they put this in phase 3. And these are the cables that are used for telecommunication, right? This is the internet cable, and it goes along the seabed and then comes in and lands at these communities. And the one that lands near Prudhoe Bay, it doesn't actually land right at Prudhoe, it lands at a Licktock Point. This is the one that we've been using to do science with. And to do that science, we have to do a whole bunch of calibration. So we have to do still a bunch of kind of old-fashioned things. So here's a picture of us doing some old-fashioned things. This is us landing on the ice outside of Prudhoe Bay in the springtime and deploying moorings through the ice to get traditional measurements. Well, not traditional in the traditional knowledge sense of the measurements, but conventional measurements of the conditions underneath the sea ice and the waves. And then we use this fiber optic cable to try to do the same thing. Here's an example down here of how well those two match up. I can't even remember which one is which color because they agree so well. But I think the orange is the cable and the green is the conventional mooring. The point is that we get measurements that are similar between the two. So how does this work? It seems kind of like magic, right? The idea is as the waves are propagating through the region, they make small pressure fluctuations on the seafloor. They're pretty small, they're almost imperceptible, but they actually cause that fiber optic cable that's on the seafloor to deflect a little bit. And we're talking nanometers, right? It's just moving just a little bit. And if we have a receiver connected to the cable that can detect these really small fluctuations in the way that the light, the optic light signal is coming down the cable, then we can detect the waves that are affecting the cable. And we can actually do it at multiple locations along the cable. So now it's like having a virtual wave buoy out far out offshore where the cable, meets the trunk cable, and then one closer to shore, and then another one closer to shore, another one closer to shore. So it's a really exciting new technology that we can sort of piggyback on these telecom installations and get some science out of these cables. The one in Oliktok is particularly good because they have extra fibers that they're not using for communication that we can just use for science. So that's been great. Here's a little bit more of an example of that work. Here's a detailed map of the cable at Oliktok Point. So close to Prudhoe Bay would just be a little bit more to the east here. And this comes out into Harrison Bay. And this is the dark blue colors are deeper water and the light colors are shallow water. And here's a case where in the fall, if you get a satellite radar image, you see some ice out here, and then a little bit of an open water, and then some new ice that'll eventually become the fast ice by the land. And if you take this little section of cable and measure the wave heights with the cable, you get waves in open water, and then a quick reduction of waves, and then no waves in the ice. And that's that same wave damping, wave attenuation that I was talking about. Now this is a way we can measure it in really fine scale, and we can do it right with the fast ice forms. So I think this is going to be one of the tools we use to really take the next leap with how the waves and the fast ice evolve together. Okay, wrap up and tell you about things that are coming in the future and when I'll be coming through the region in the future. It's 2025. I'll definitely be there to to get on and off the ships a little bit, and also do more aerial deployments of the buoys. So probably May or June of 2025, we'll put more buoys out from the airplane. You may see them watch up on the beach. Just let us know. And we'll use the ships also and put out more buoys. We're working on a proposal to expand that program in the Bering region to include more ecological measurements. We've got a lot of local partners in mind, and harmful algal blooms are definitely one of the things we're really targeting with that. We're also doing a lot more work up on the slope. So I'll be going to Reykjavik next week to talk to folks about planned field work in the springtime, spanning 25, 26, 27, and trying to understand how the landfast ice evolves, and then when does it break out, when does it go away. And then we also have another project that's back to that cable location I was just showing you, and that'll be next fall, so like a year from now, and looking more at how that landfast ice starts, how does it form, and how does it protect the coast in the fall. Okay, with that, I'm happy to take questions, and always available offline too.
All right. Well, thank you, Jim. And I see we already have a question in the chat. We'll get to it in a sec, but for everyone thinking of your questions, know that this is a good time to give a little love in the chat box for Jim for taking tonight to give us this talk. Actually, I forgot to mention he's in Seattle, so he's actually staying up even an hour later than us to do this, and he's doing this for our benefit, and we really appreciate that. So show a little love in the chat box. It's never easy to be a public speaker, and it never is. And you rocked it. So thank you, Jim, for that. So the first question in the chat is, how deep is the cable, the quintillion cable?
Mm. Um, when they installed it, they actually trenched it. So they had this, it was a big operation, right? And they cut a little slit in the seafloor and laid the cable into that. And the burial depth into the sediment is 2 meters, 6 feet. And then in terms of the seafloor topography, the bathymetry, it comes all the way up to the land, so zero, and then it goes out to sort of the middle of the continental shelf, so 30 meters, about 100 feet deep is where it makes those junctions. Obviously, a little shallower in some of the spots where it comes through the Chukchi or out of the Bering Strait. That's pretty shallow there. But I think, yeah, the offshore part that wraps around Alaska, that's all in the kind of 30 or 50 meters. And of course, many of you are familiar in 2020. I'm losing track of the years so quickly here. 2022 or 23? No, it must have been 23. The cable was cut, right, by ground a piece of ice. So that was a little bit of a shock where they thought they buried it deep enough, far enough, but not far enough, and you get a really big piece of ice coming up wind with a deep keel will just kind of plow a trench through the sediment in the coastal zone and take out the cable. Anyway, they fixed it. I'm sure you all were aware of that.
Took a while.
Yep. Yeah.
But for Nome, it was worse because the outer communities already had the Starlink.
Mhm.
That proved to be a winner.
Yeah, that's a game changer for sure.
It
In
is a
our
game
work, it's
changer.
also a game changer. Yeah. Although it means I can no longer concentrate anywhere.
All right.
Um,
Let's see. Is the wave data you get from the quintillion cable publicly accessible? This is from Ellen Jessup.
mm, it
Thanks so much.
is, but not in real time. It takes a while to process it. It's a lot of data. I mean, terabytes of data. So the stuff from 2022 and 2021, that's all up and public. And you can just reach out to me via Gay, and I'll give you the links for it. And I think we have put up the 23 data, but not the 24 so far. So it just takes a while to do all the processing, get it up. But definitely, the intention is to make it all public. It's in the Arctic Data Center, if you're familiar with that. That's a big central repository. That's a pretty good one. If you're ever looking for data from a particular region, you can. It's got a nice interface. You can click on a map and say, "I want to know everything that's ever been measured in this box." And the Arctic Data Center is a good place to do that.
All right. I'm just typing in here. So if people want to, here's my number.
Yeah, I'll put mine in too. Um,
And you've got some nice kudos. Thank you, Leandra.
Thank you.
That was a nice one for Jim, as well as everyone else who did that. Um, for the folks in the region, now he showed those pictures of those tubes. How big are those micro swift
Hmm.
things that you're jettisoning out the bottom of
Jettisoning,
the
yeah.
whatever the what is that plane? A twin otter.
It's a twin otter. Yep.
Lower twin otter.
Yeah, that's
How
the
big are
tractor
those
of the
roughly?
sky.
2 feet,
Um,
3 feet long?
yeah, two
About
feet.
like this?
Yep. Yeah. Let's see, 3-inch diameter and
Okay.
30 inches long.
And
So
because just
easy to hand carry. If you were walking down the beach and you found one, wouldn't be
if
any trouble to pick it up and carry it. They
you
weigh 6 pounds.
you might want to put an American flag on those tubes, and I'm not kidding there. We're people in this region, there's a lot of different countries coming up, and um we're not you can't get
Mhm.
data from the other side, or you have to kill your machine, I think. And same for other people. And if their machine is in our waters and it doesn't look like it's an American equipment, it may be taken out by somebody else, one of us.
Mm.
And so or reported to the authorities. So we have a lot of things in the region that are swimming around.
Yep.
When you said those came near Nome, we actually had it come right up against Savunga. So actually people mobilized to try to
Mm.
find your buoy. And then there was one buoy that was found and reported, although I think the individual didn't know what to do at the time because we hadn't heard you talk. And it was up at Tin City. One actually came
Yeah.
ashore and he took a photograph of that.
We actually we got that one back from one of the workers at there. It was found again, so it must have been pretty like obvious on the beach by one of the workers at the radar station. Um,
Oh, at Tin City. Okay.
yeah.
Yeah, in that case, give us some feedback on that if one is found, because it would be
Mm,
a good um of interest to everyone in the region, what that
mhm.
was, who found it, what it was doing, in case other people see another one, because it looks like
Yeah.
the aircraft is spitting those out, more than
Yeah.
one.
I mean, we're still never going to do like huge numbers of them because we just, we don't have the funding for that. But, we've been doing 6 in the spring and 6 in the fall. That's what we're planning to do next year. Um, so it's enough to, get coverage of the overall regional patterns, but it's not enough that you're never going to see like hundreds of them on the beach or anything like that. I mean, if we were
No,
going
but
to do that, we'd come up and
two of
pick up our own
six,
pass.
two of
Yeah.
six came ashore, so
Yeah,
the
that's
odds,
true. Good point.
yeah,
Yeah.
the odds of it, and who knows what the Russians think when they find one of yours, they probably get rid of it.
Yeah.
All right. And then Leandra D'Souza asks in the chat, how do you secure the mooring in the high Arctic in the open water when the ice is gone? And you might want to describe what a mooring is for all of us here.
Right. I mean, the mooring has an anchor at the seabed, which is very heavy, right? Thousands of pounds. And then from the seafloor, line coming up, and then the instruments and the flotation are above that. So I think the simple answer to Leandra is just a big anchor. That's it. Just like you're mooring a ship. The difference is that when because we want it to survive when the ice is there, we have it end up just below the surface, which you wouldn't do with a ship, obviously, right? So we measure the line just right so that once we drop the anchor, it ends up just below the surface. And then when we want to get it back, that's an important trick. There is an acoustic release. So we send a command acoustically, a little sonar ping. It's very short. It's just like saying, hey, hello. And that triggers a release that opens, and then it sends line to the surface, and then we can pick it up. So that's pretty clever, but pretty standard now.
And then you attach your equipment to that string that's going
Yep.
from a buoy to an anchor, and your
Yep.
stuff's attached to that below the water.
Yep.
Yeah.
Yeah.
3,000-meter line, question mark.
Yes. 3,000-meter line.
So that would
Yeah.
be up in north of Utqiagvik, where the
Yeah,
shelf
exactly.
falls
Yeah.
into the deep
Yeah.
water. Yeah, I
Yeah.
agree,
So just
Leandra.
that line
Wow,
alone
that's
can be,
a lot of
we
cable.
usually, yeah, it's a lot of cable. We have these huge spools, and they're about the size of a truck. We have 3 of those. That is all that line.
And then do you have any of those moorings with equipment in the much more shallower Bering Strait region?
I do not, but Rebecca Woodgate does. She's been doing that for a long time in the Bering Strait, and a lot of what we know about how water is moving through the Bering Strait is from her work, and a lot of that's done by Norsemen too, who you would see that boat a lot in Nome, right? Um, and but that's much shallower, right? I mean, 50 meters, 100 meters, so. And in some ways that's easier, but I would never say nothing's ever easy in the ocean. The ocean eats things. The ocean doesn't care about your gear or your science. It's harsh. So I think she's collected a remarkable amount of data over the last 20 years, really understanding the Bering Strait with pretty similar moorings, just much shallower.
And so, we just had, well, first I better say, any other questions from the audience on the wave science that's looking at how that's affecting our coastline? And ultimately, Jim, what do they do with this? I know it's the models, so the modeling is trying to make predictions based on the best information. Are there any other uses or any other groups that would use this information?
Hmm. I mean, certainly some of the data comes in real time. So things like the backyard buoys. I mean, this data can be accessed if you just want to know what the waves are, and because you're about to head out fishing, then you could use it that way. Uh, which is, I think that's very useful as someone who spends a lot of time out on the water. But I think, being able to forecast these things, I think, is probably one of the biggest uses. And then also just having a historic record of what the data was, so you can um, design new coastal structures and new infrastructure to meet those conditions and whatever ones are coming in the future. So again, if you're going to change the dockhead at Nome, you've got to make those decisions based on something: how high, how wide, how big, and the waves that are coming in to the region. That's one of the parameters that goes into that, right? There's a lot of other things that go into that, but the better the information in, the better answer out usually.
So would we get any of those? I mean, you're working some of this through those micro swift buoys in the region,
Mm.
right? For the Bering Strait
Yep.
region. And then we
Yeah.
just had, and I know you're unfamiliar with it, but the region was rocked pretty hard the third week of October. I don't
Hmm.
know, I'm sorry to the people up north, I don't know beyond Kotzebue if that had any big effects, but it certainly put Kotzebue underwater, and Shishmaref lost a lot of ground. People have lost a lot of gear and boats. Um, is that the sort of thing that your work would be helping predict? So that, I mean, that was really extraordinary. We had Kotzebue went underwater, the runway and everything. So and it was an unusual storm, meaning it was so far to the west that I think it was about 800 miles away from us, and just forced all that water in from a distance from one side of the Chukchi to the other. Same
Right.
for down here in the Bering Strait region. So people could use that for maybe predicting these kind of events. Or like at St. Lawrence Island, I know that these storms are eating up or changing the shape of the beach, so
Hmm.
that it sounds like the dump can get wet sometimes, and things, or the
Hmm.
runway, which is close to the ocean, can get rocks thrown up on it or gravel thrown up on it, and it takes extra to remove all that. Or if you have a dump that's getting inundated with water, that's probably not a good thing for the ocean or for St. Lawrence Island. Are
Right.
these the kind of things that this data is going to help communities
It,
be able
it
to?
should. I mean, it should. We can use it to improve those forecasts, not um, that forecast that just happened, but basically tell the forecast how wrong you were, and then you can do analysis on, like, what do we need to do to get it right. Right now, sometimes we call that a hindcast instead of a forecast. Right, you're looking backwards, but when you're looking backwards, then it's like redoing a test you failed. Right, you're like, well, I'm going to learn something from how I failed that test. Right, I'm going to go back and see what questions I got wrong and see where I got them wrong, and then that's going to make me do better on the next test. Right, that's the idea.
Yeah. And so that would be for the agencies. Ultimately, they'll be picking up from this, and like the
Yeah.
National Weather Service will be able to give us a more
Right.
accurate forecast. Okay.
And that's exactly right. But unfortunately, it does take time, right? I mean, you have to accumulate a bunch of these things. So I don't. It's not going to make the National Weather Service, the Alaska desk, better next year immediately, but over time it will.
And Leandra added in the chat box, FYI, thanks, Leandra.
Mm,
FYI, in relation to the data presented here, we had a flooding
mm,
event that almost breached our fresh water source. Wow. On October 7th, 2022, in Utqiagvik, approximately 20 days after the hurricane, that would, I think, Merbach, in
yep,
the
we're back. Yeah,
Alaska northwest coast. Oof, that sounds serious, Leandra. If your fresh water was almost breached by the sea, that would be hard to fix that problem.
yeah,
Oh,
that's a big problem.
that is a big one. All right. Well, thank you again, Jim. Any other questions from the group? So for the next Street Science will be on a Wednesday, November 20th, and that we're going to have the U.S. Marine Mammal Commission. And we're familiar in this region with the Fish and Wildlife Service that have research and management authority over, what did I say, fish and wildlife, bears, polar bears, and walrus. And then NOAA, Department of Commerce, has authority for the management and research of all the seals, all the whales, and all the sea lions. Those two agencies we're familiar with. Overarching for both of those, there's an oversight agency called the U.S. Marine Mammal Commission. And one of the 3 commissioners in the country will be giving us a discussion, an introduction to what is the Marine Mammal Commission, what's their job, and how do they oversee some of the policies and actions that the Fish and Wildlife Service and NOAA both give our region when it comes to management and research of marine mammals. So that'll be a very interesting one that's coming up on Wednesday. And I'm sure they'd like to hear thoughts on how it's working. And I'm sure there'll be lots of questions. Hook. Charla asks, can you name our next storm?
Ooh. I got nothing. Sorry. But it's coming. That's for, and there's another hurricane down in the Gulf of Mexico too. Like the storm season just won't end.
Yeah. Well,
Yeah.
we're supposed to get something next week, I think.
Yeah.
We'll see how that unfolds. I think around the 14th or 15th. Yeah,
Yep.
I like the unhappy or the upside down smile. All right. With that, Jim, if you can stay on, we'll let everyone else go. And we thank you all for coming to Straight Science, and we'll see you next on the 20th, a week from Wednesday. Have a good night, everyone.